Yeah, screen share is enabled. Now you can share the screen.
Like this one, right?
Okay.
Can we use this one as a two connector pin?
Yeah, can just once go to 2D simulation. Let me check that.
I haven't assembled the components
Yeah,
here.
yeah, no worries, no problem. Yeah, once click on design, uh, update PCB. No, no, no. Wait a second. Wait a second. Import changes from schematic. First option. Yeah, click on apply changes. Yeah, now again control S, and then go to click on either 2D or else go with the 3D option. There is no necessity that we need to update the schematic only after uh,
Yeah.
completing the entire schematic. See here you have the those things, but the connector pin is missing. As if you just check, 3D model is missing.
Yeah.
So that's why that means the part that you are trying to put, it's not the correct part. Actually, what we are looking for. Okay,
Okay.
so you can try with some other pin. See, just
Yeah.
open new tab and type for just open new tab. Okay, and type 2 pin header, 2 pin header space LCSC. Yeah, click on that. Here you can see the 3D models also, right?
Yeah.
Yeah, just look for the pin which is having 2 pins.
Okay.
Okay,
Sure.
this is having 3 pin like that. Just look for the component which is having 2 pins.
Okay. Okay.
Or else here also we are having a search bar inside LCSC. There
Yeah.
are, yeah, there also you can type 2 pin connector. Yeah, first one headers, header mail pins. Yeah, see these all are different kinds of 2 pin connectors.
Yeah.
So you can scroll little bit down. Still, see these are all different types. So here you can pick whatever the, see all components will be available. Only we need to patiently look for the component, right component.
Okay.
So all components would be available in LCS. We need to look just patiently. We need to check for the correct component. So it's a huge repository. Sometimes whatever the component we are trying to look may not be immediately available. So we need to use filters, try searching with some other keyword. So like that we
Yeah.
can find out whatever the component that we want.
Okay.
Yeah.
Thank you.
So usually 3 pin connectors are widely available. Okay, compared to 2 pin connectors, 3 pin connectors are widely available. So even if you want to use 2 pins only, you can add one more pin, 3 pin. Okay, let's say one is VCC and another one is ground. So you can put one VCC and two grounds like that.
Understood.
Yeah, because usually we need to have at least one more ground extra, additional ground. Usually, because with a ground actually compared to VCC, ground plays an important role in data communication. So there is something called common ground. So you can also look into it if you want more information about common ground. So unless there is a common ground path between microcontroller and the sensor, so data cannot be exchanged. No matter even if you are using serial clock and serial data or I2C buses, still I2C also require common ground microcontroller, and that means the grounds of the microcontroller and the ground of the sensor. So we need to connect it together. That we call it as the common ground. So once if one ground is shared by both microcontroller and its slave, then only data can be transmitted. Though the actual data transmission is directly through the I2C lines, still common ground is required. Without common ground, I2C address is not detected. That's why people put one additional ground. So that's the importance of the ground. Yeah. So now we will be discussing about. So this session is about ESP32 and how to use two cores. So last time we started the session, but due to heavy rainfall, I am unable to continue the session, and we ended the session finally. Now we will be discussing about uh, how to use two cores in ESP32. So just a few minutes ago, we completed one more session, like another batch, where we discussed about uh, CRC. So CRC means cyclic redundancy check. Uh, it's one kind of checksum validation that we discussed in the Arduino class. Now we'll be discussing about how to use two cores in ESP32 to increase the efficiency and to run the activities at a time asynchronously and non-blocking. Yeah, I'm just looking for the right PPT. Just give me a second. Yeah, I will be sharing my screen. Yeah, so today concept is multi-core mastery. Okay, programming simultaneous tasks on the dual core ESP32 architecture. So one is simultaneous, so that means we are running the task simultaneously, both will be executing at a time. Okay, and another kind of task can be executed either sequentially or simultaneously. So by default in Arduino or many other microcontrollers, usually the program executes uh, you know sequentially, but not simultaneously. But in Arduino we are having two cores, so on one core you can run some tasks and another core you can run another task. Already we discussed in the previous session like what kind of tasks can be executed usually by default. Okay, by default there are total core 0 and core 1. It's like a two CPUs, and we also discussed that these two cores are identical in nature. Okay, they are non different, I mean they are identical in nature. So in terms of architecture they are same, but one is designed to handle Wi-Fi stack, Bluetooth, internal radio, that means completely related to the RF radio frequency. It operates complete related to the RF, whereas the another core is specifically designed to execute the program which we declare in setup function and loop function. So this is by default allocation of the tasks, okay, for core 0 and core 1. But through program you can still assign one task to one core and another task to another core. That can be achieved. So by default, core 0 handles the Wi-Fi, Bluetooth low energy and radio frequency related activities. So one more thing that we discussed is that if you want to use this kind of two core, okay, if you want to utilize these two cores, then you need to take help of this freeRTOS library. So you, like just like to use the non-volatile storage, we have taken the help of NVS underscore flash library. And similarly in Arduino, if you want, just like NVS, just like we have non-volatile storage in Arduino, sorry, in ESP32. Someone trying to join the meet. Okay. So just like we have a non-volatile storage library in ESP32, similarly we have EPROM library, electronically erasable, programmable read-only memory. So it's just like equivalent to NVS. So that is there in Arduino. Okay. So similarly, to utilize dual core functionality, we need to take the help of freeRTOS library. Okay. Real time, where RTOS means real time operating system. Real time operating system. So this is a part of ESP32 ecosystem. We are having so many libraries. This is one part of ESP32 ecosystem. So now we will be jumping into fundamentals of freeRTOS, some basic terminology. Okay. Uh, yeah. So freeRTOS library plays an important role if you want to allocate task scheduling. Everything is can be achieved through freeRTOS library. So here we are discussing two things. One is pre-exemptive scheduling. and another one is memory isolation. So the first one is pre-exemptive scheduling, second one is memory isolation. So as you can see the description over here, I will read it out. The kernel uses a tick timer, okay, tick timer, 1 millisecond by default to convert to context switch between tasks. High priority tasks can interrupt lower ones instantly. And I'll read out the memory isolation and I will give my interpretation. Yeah, someone trying to join. Yeah. So we are discussing about free RTOS library, free real-time operating system library, through which we can run two different tasks on two different cores. Okay. So which is very responsible for simultaneous task execution. Okay, not sequential task execution. So we can run different tasks at a time simultaneously on different cores. So for that we need to use free RTOS library, under which we are discussing about the fundamentals. So first we are discussing about pre-exemptive scheduling. So kernel is something like at lower level. Okay, so basically we at Suchna we actually design Linux kernels. So what does kernel mean? So kernel is something like which is which controls the operating system. Okay, complete the entire. I will show you. The kernel is the core component of an operating system. It acts as a bridge between the computer's hardware and the software application running on it. When you open any app, okay, the kernel grants it access to necessary resources like CPU time, system memory, and input-output devices. See, kernel is something like equivalent to the operating system. Okay, like it is a part of operating system because operating system we are having many things like bootloader. So bootloader is there are many programs that come by default in the system. Okay, whenever you buy a laptop, so some programs executes during the whenever you start your your PC, or else whenever the operating system is you know is came into live. So immediately the first instructions which will get executed, those we call it as bootloader. Okay, bootloading program. So this kernel is one component of operating system. Operating system have multiple things like bootloader, kernels, like that. So many are there. Linux bundles. Okay, so many are there. Flash files. So this kernel, whenever see whatever the task that any app, see whenever you open an app, it requires so many permissions. Not only restricted permission like location, camera, microphone, or something like that, but internally also it need to get many resources from CPU. See, memory itself, whenever you open any app or see even to install any app, you require some space, right? That means the kernel is something which grants the memory access. Okay, kernel is responsible for managing everything. So we at Suchna, we having the technology to build Linux custom operating systems completely at completely designed at our Suchna. Okay, in-house, completely in-housely designed, built, tested, and we did so many tests like penetration tests. So after doing so many tests, we finally released those kernels. So already you came to know that we recently our team posted one message in the PCB designing group that we will be very soon releasing one wristwatch. Okay, so basically even that wristwatch is powered by Suchna operating system. We named it as Fluxer OS, which is operating under Linux operating system. It is completely, the OS kernel is completely designed by us, me and my colleagues. Okay, so even the ESP32 is also having a kernel. Okay, because ESP32 is also a CPU in the sense because it is having two cores, core 0 and core 1. So those cores are nothing but two different CPUs. Okay, dual core processor, 32-bit dual core processors. Okay, and yeah, so coming back to here, so every there would be something like a tick timer. So tick means tick 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 tick, like that. So every 1 millisecond it can calculate. One tick means there would be a formula to which we can determine number of, from how many ticks is equivalent to the time equivalent in terms of milliseconds. So there would be a conversion and there would be a formula. So there would be a tick timer through which it can detect the time. Okay, and context switch between tasks. So you can switch between the tasks. So and there is also priority order. So that means, let's say you have assigned two tasks to one core. Okay, you have assigned see, if you assign one task to one core and another task to another core, so though both these tasks can be executed at a time. They may be executed at a time. But if you assign two tasks to only one core and one task to another core, so now the for the core to which you have assigned these two tasks, so for these two tasks you need to specify the priority order. What should be executed for the first, and what should be executed in the begin, I mean initially, and followed by like it's like a predecessor and successor. Okay, so what should be executed uh, at the predecessor, that means a previous one, and after once this one the initial task is executed, then the successive tasks can be executed. So this can be achieved by allocating the task priority. Okay, so here one important point that you need to understand is that, so should the task priority should be should we give the higher ranking or we should give the lower ranking? This is very essential to understand. So it is clearly we are indicating over here in the note that higher priority tasks can interrupt lower ones instantly. Higher priority tasks can interrupt lower ones instantly. So what does this mean? Can someone able to explain that higher priority tasks can interrupt lower priority task instantly?
Like the major part which needs to be accomplished might also, I mean, like it stops the lower preceding one,
Yeah, right.
low ordered
So
one.
yeah, so higher ranked, higher priority task overrides the lower priority task. Okay, so if you give higher ranking, it will be executed in the first. Okay, then your it follows the order. So it's like something like big to small. Okay, so small to big we call it as ascending. So big to small, it means descending order. So it basically it follows descending order. So it start executing the tasks which are having the highest priority, and it goes down till the whatever the function which is at the end having the lowest priority. So highest to lowest, that means it follows the descending order. So this is very essential to understand. Unless you know that, see, if you know your that we can run two tasks or there is something like a priority order, unless you don't know whether you need to give higher priority or lower priority, then there is no, you cannot directly implement. Okay, there is no use of learning about this. So that's the important point. And coming to the memory isolation, each task is allocated its own private stack memory. This ensures that a function call deep inside one task doesn't corrupt another. Okay, now you might have a question that if I directly assign two tasks to a same core, will there be any possibility to corrupt the another one? No, because see, the manufacturer expressive company is not a normal company. They are highly experienced highly experienced experts. Okay, so they designed in such a way that they implemented the memory isolation. So each task is having its own private stack memory. It cannot go beyond its stack memory. Okay, for every task there would be a separate stack memory. So this ensures that the another calls, okay, it could be like no matter whether the execution is altered due to because of rankings. So higher and lower ranking functions, no, existence of that, no matter whatever the circumstance could be. So memory is isolated. Each task will be having its own private stack memory, so that the uh, the data, the memory which belongs to the another task is not corrupted by default. Okay, unless there is any hardware catastrophic failure. So by default memory isolation is there implemented in the ESP modules. Okay, so we discussed about the pre-exemptive scheduling, so where we learned that higher priority tasks can interrupt lower ones instantly. And in the memory isolation, we understood that each task is allocated with its own private stack memory, so that the calls to the another task does not corrupt the memory of the another task, because uh, the memory locations are different. Okay, So each one is having its own individual private stack memory. It's not a shared one. It's completely individual. It's individual. It's not a shared one. Okay, it's like something like a private public. So if you take a private, if you want explanation in terms of private public, so having every task is having its own private stack memory, not public. Public is commonly shared. So any task can share its memory with the another one. But here it is private. So every task will have its own private stack memory, which cannot be uh, corrupted by the another task. Okay. Yeah. So now we need to learn how to create a task. Okay. How to create a task. So this is the primary function used to register a new task and bind it to a specific core. So if you want to bind as any function, see, binding is nothing but you are assigning this particular task to be executed uh, to a particular core. Okay, or giving that responsibility to some core to execute this particular function. So we call it as a binding. Okay. So or else we can also call it as pinning to core, pinning a task to a core, or else in simple terms binding a task to a specific core. Okay. So this is the primary function. X task create pin to core. xtask create pin to core. This is the main function which is used to bind any task to be executed to any core. Okay. So it is accepting multiple parameters, as you can check over here. The first parameter is the task function, and the second parameter is task name. Third parameter is task size, and fourth parameter, it accepts a null string. So we'll discuss why null to be passed over here late in the later session. And the next one is priority. That's what we discussed in the pre-executive scheduling, that for each and every task to be executed, you need to assign some priority order. So based on this priority order, that core we can be able to determine which task needs to be executed with high priority. Okay. And yeah, based on that, accordingly, with the descending order of the ranking system, priority ranking, the functions will be executed from highest ranking functions to the least ranking function. Okay. So and the third parameter is stack size. So I already told you that each and every task to be executed, it will be having its own private stack memory. So here you can explicitly define how much of stack memory that this particular function can utilize maximum. Okay. So if you give a smaller value, but if the particular task is consuming higher stack memory, so this will causes data overflow error, because the data that the memory that the particular task is consuming does not directly fit in this particular stack memory. Okay. So that's why you need to decide this stack size based on the task that to be executed. So you cannot blindly give a random value to the stack size. So it is dependent upon the memory consumption by the particular task to be executed. So and you know about the priority order. Okay, highest priority, highest ranking, and least ranking. And the next parameter is task handle. Okay, next parameter is task handle. So we will discuss about that. And the last parameter is core ID. So every core will have a core ID. Okay, so if you are having three cores, so in microcontroller it will have three core IDs. So this core ID is used to uh, because this function need to determine that whatever the function that you are passing to it as a parameter, that you are passing the argument to a parameter, so to which core it should be assigned, the task to be binded with which core. So the function should be able to determine that first. So that's why the last parameter, it is accepting the core ID. So whatever the core ID that you present, that you pass over here, unless if it's a incorrect value. So if it's a valid core ID, then the task will, whatever the task function that you are passing over here, okay, that will be assigned to this particular core. Okay, it can be core 0 or core 1. Okay, this task function will be assigned to this particular core, and this core will be able to execute those functions depending upon this priority order. Okay. And while this task function is being executed by this particular core ID, so this task will be having its own stack memory. Okay, where it's a private stack memory, which can be accessed by this particular function only. Okay. or this particular core, or this particular task. Okay, yeah. So now this particular memory, which is this particular stack memory of this particular function, cannot be accessed by default by another functions. Okay, so whatever the maximum threshold maximum allowed stack size, okay, allocated stack size, that you can pass it over here. Okay, beyond this stack size, memory cannot be accessed. Okay, it causes data overflow error. So if it's less than this stack size, no issues. If data is underflow, I mean, it's actually not underflow, it's in the normal range. But if it is greater than the stack size, it will definitely cause an issue. And then this particular task name is just like an identifier. Okay, it's just an identifier, just a name. So so I hope these parameters are clear, right? So can you just confirm if the parameters are clear? Are you clear about the parameters, everyone? Can you just quickly react with thumbs, everyone, so that I can understand and I can proceed further. Because if you don't understand, I need to repeat. Yeah, Anurag, are you able to understand? Okay, yeah, we'll continue from where we stopped. So these are the different parameters that this particular function is accepting. Okay, x task create pin to core. So now we will discuss uh, how many of you remember, how many of you attended that NVS session, non-volatile storage session, where we discussed about NVS handle? Anyone remember about NVS handle? NVS handles. We discussed about NVS handles. So anyone, if you just remember, can you please explain in your own words what we discussed during NVS session about NVS handles? See, handle, it's actually the same handle, but the kind of what the handle deals with, okay, that varies. Yeah, Sri Krishna.
Like we used NVS underscore handle T and kept any name to handle that particular function, like a
Yeah,
point of contact.
yeah. So we said that handle is responsible for all read and write operations. Okay. So if you see, we are having a function like NVS open function, right? So in NVS open function, we can pass the handle as one parameter and the permission mode, whether you want NVS read only or read write. So when you pass that handle and the permission to the NVS open function, then immediately the handle will be getting access to read the particular. We also discussed about namespace, storage namespace. So immediately the handler will be granted with the access permission that you describe in the NVS open function, and it will be giving the access to that namespace, whatever the permission that you describe, if it's a read write or read only. So that means all the read and write or all operations, okay, memory operations which are related to non-volatile storage memory, that can be achieved only through the handler. So as the name suggests, handler means it is handling everything. Okay, the same analogy can be applied to here as well. But here what we are discussing, it's not an NVS handler. Okay, so what's the present handler we are discussing about? Task handler. So that means task related things, everything can be managed through the task handler. Just like as we manage the read write functionality in the NVS handler, similar analogy can be applied over here. So as you can see over here, so the task name, okay, whatever the task name that you are passing, it should be a human readable name. The second parameter is a string name, blink task or something like that. Okay, it's just purely for the debugging purpose. Okay, it does not carry any kind of other things, so it's just purely existing for debugging purposes. Using, there are some v task list and those kind of functions through which we can debug a task. If any let's say if the task is not executing properly, or you want to change, or you want to monitor activities that are related to that particular task, then so it's like a human readable name. Okay, and whatever the task that you are passing through the x pin x create task pin to the core function, pin to core function, the task must be a void, that must be a void function. So what's a void function? So void means emptiness. That means it should never return any value. All the functions which never return any value are called as void functions. So the task must be a void function if you want to run it asynchronously. Okay, I mean simultaneously. And it should contain a human readable name which you are passing it as the second parameter. And it is only for debugging purposes, troubleshooting and debugging purposes. Yeah. So now we are discussing about core affinity pinning. Okay, core affinity. So here we are having uh, three things, right? Core 0, core 1, and if you don't specifically indicate the core that you want, automatically the task scheduler will automatically move to the like whatever the core. See, let's say core A, core 0 is already in some process, it is already in stress, whereas core 1 is little bit free. Okay, then this task scheduler will automatically assigns this particular task to the whatever the core which is free. Okay, so that is the automatic task scheduling if you do not specify the affinity. Okay, no affinity. But if you specify the affinity means the particular value that you are specifying over here. We usually, technically here it's just a technical term, core affinity. So if you pass the core affinity as 0 or else 1, usually core affinity 0 is used, core 0 is used for time critical calculation. Okay, time critical. That means it must stay away from user UI logic. And for core 1, the standard the standard processing, like whatever all other things other than the time critical functions, rest all can be uh, pinned to, or else you can pin it to the core 1. Okay, so now we will see program examples. Okay, after program examples we will conclude today's session. And moreover, tomorrow there is no class for ESP and as well as Arduino as well. And the timings also we are changing due to some other circumstances. We are changing the class timings from afternoon to the evening. Exact timings will be updated by our team shortly in the group. So according to that time, kindly please follow and cooperate with us. Okay, now we will be jumping into the program examples. So now let's see few program examples. Okay, already we discussed, those who attended the Arduino class can just raise your hand. Those who are already enrolled into the Arduino course. Arduino. Ibrahim is there. Shikaran is also there, but she is busy with the class. Yeah. So Ibrahim, you might have remembered the earlier example where we discussed the blinking of an LED, right? I think you have already worked on it. Initially, you faced some issue, then you said, yeah, I figured it out, and I told you whether it could be, uh, there could be multiple reasons, like you need to check whether the GPIO pin that you specified in the program is actually the pin that you are connecting with the LED. Sometimes, usually, we may declare a wrong pin in the program and we may connect it to some other pin during wiring. And second thing reason could be loose wiring. And third thing is sometimes jumper wires may be damaged internally. And fourth thing is never directly connect LED with the any microcontroller, any power supply. Always use a current limiting resistor. Usually the resistance varies from 220 ohms to 1 kilo ohm. You can use any resistor of resistance varying from any resistor, okay, which is in the range 220 ohms to 1 kilo ohm. So standard usually we use 220 ohms, sometimes we use 1 kilo ohm. You can use within this particular range. And when you change the resistance, the brightness or intensity of the LED will also change. So these are different things that usually causes the LED not to work. So where we discussed about blinking one LED and two LEDs as well in the Arduino program. But what actually happened, if you want to try to run, let's say we try to blink one LED at some time, let's say at every 1 second, and we if you want to blink the second LED for every 2 seconds, what happened? Both these actions are not executing at a time. First, the first LED is blinking after 1 second, then the timer for the second LED starts of 2 seconds. But what actually should happen? The timers for both these LEDs should start at a time. Okay. So during our earlier program where we discussed, that's not simultaneous execution, it is sequential execution. So simultaneous execution you can achieve it in ESP modules because you're having two cores, dual core processing units. So now yeah, the first example is to blink two LEDs simultaneously. That means the timer for these two LEDs should start at 10. Completely non-blocking execution, no delays, independent timing cycle. This is what I said, independent timing cycles. Okay, so one LED should blink at 500 milliseconds on core 0. Okay, and another LED should blink at 1 second. Sorry, and another, see, this is task 0. Task 0 is to blink LED 1 at 500 milliseconds interval on core 0, and task 1 is to blink another LED 2 at 700 milliseconds time interval on core 1. So two different cores, two different tasks, two different time intervals, but independent timing cycles and completely non-blocking execution. Both timers will start at a time, and everything happens simultaneously, not sequentially. So that's why for that we need to use multi-core processing. So this is what we need to do. Okay, basic in the setup. So this is the main code. Okay, so in this particular code, so usually if you want, see, uh, so today I will be giving you a small assignment. Okay, because further if you want to learn further these things about, see, today I just explained you about the priority order, the different parameters that the particular function can accept. So before I explain about all these different function, I mean different examples on program, so I would like to give you a small task. So where you need to research about vtask delay function. Okay, vtask delay function. So I already told you that there would be a tick timer inside the core of the microcontroller. There would be a tick timer, so which can detect the time. Okay, since the timer has been started, since you initialize began the timer. So how much time has been already elapsed? That can be determined with the help of a tick timer. So now today the task is to research about vtask delay function. Okay, vtask delay function, and with this particular function how to determine how much time has already been elapsed, I mean not elapsed, or else how we can delay the program which is being executed for a certain period of time by using vtask delay function. So this vtask delay function is very related with the tick timer. Okay, and everything, the calculation usually in milliseconds. So now your task is to research in about a vtask delay function, and you can submit a handwritten notes, or else you can submit a PDF in the group, in the WhatsApp group, and I will be reviewing that. And then in the next session, we will be discussing about how to run two different tasks on two different cores simultaneously with the help of a task scheduling. Okay, with the help of this vtask delay function. Okay, I hope today's session is clear, right? So can just quickly react with thumb so that I can wrap up the today's session. Yeah. So Ibrahim, hope you understood, right? Okay, fine. So thanks for confirming. So this is today's session, and I am your expert mentor Hemant from Suchna, signing off. Bye bye. So see you soon in the tomorrow session. So be ready with your uh, research work, and also we are having one more session during this weekend. Already we gave projects for the PCB design batch. Okay, those who are already there, Sri Krishna and Ibrahim, Shikaran is also there. So you can be ready with your project. It's not necessary that the project should be completed, but you need to show your progress. Okay, I will be reviewing your progress, and if you have any questions in PCB designing, I will be taking an additional hour on this weekend. You can ask all your questions, and I will be answering them. Okay, thank you. So already the video is being live streamed. As soon as the session is over, we'll post you the live recording in the group. Thank you. మనం మాయాపూర్ వెళ్ళినప్పుడు ట్రాన్సాక్షన్స్ వచ్చింది కదా, అమౌంట్ ఎంత అయింది అడగరా? 15K. ఇప్పుడు ఇప్పుడు ఎందుకు పెట్టంటే ఒక ఇంటర్నేషనల్ వాడు ఉండు నైజీరియా నుంచి. అప్పుడు చెప్పే ఒక 7K నాకు పంపాలి ఇంకా. ఇంకా నాకు ఇంకా 7K రావాలి, ఇంకా రాదు.